So good afternoon, everyone. Welcome to the latest edition of the webinar on behalf of the SMART Initiative. And it is my pleasure to introduce today's speaker, Dr. Satish Sankaran, who is the EVP of Engineering at Exacta Digital Labs. And he's had more than 20 years of experience in the upstream and downstream industries in a variety of roles, technology development, consulting, project execution, management, and of particular interest to us is his work in digital oilfield technology and reservoir management and how that relates to optimization of oil and gas production in both conventional and unconventional reservoirs. So he's worked in Halliburton and Anadarko before joining Exacta. He's also an active member of the Society of Petroleum Engineers, and he's the lead author of the recent SPE technical report on data analytics in reservoir engineering. So without any further ado, I'll hand it over to Satish, and we're very excited to hear about his thoughts on the fusion of analytics and physics. Satish.
Thank you, Srikanta, for the introduction and also for inviting me today. Can you all hear me okay?
Yes.
All right. I thought I'll probably start with a news article that I read recently that I thought was very interesting. A few hospitals in Asia are now using an AI tool to actually quickly analyze CT scans of COVID-19 patients. An algorithm was developed by a company called Axial AI that can analyze a CT image in under 10 seconds. And this has helped all the doctors across many hotspots, especially to treat thousands of patients much more effectively, especially with a unique and a quantitative view of the trauma that is happening in some of these patients' lungs. I was curious to see who else was using this, and it turns out some of the British hospitals are also now using AI tools to scan hundreds of X-rays. They didn't use CT scans because they are expensive, but X-rays are not as high resolution, but they are still trying to make use of some of these tools to treat their patients swiftly and very efficiently. This is serious stuff. People's lives are at stake, and the success of some of these methods are actually helping these hospitals quickly make decisions on whether to admit a patient or to send them home, and this is the way in which these countries are actually dealing with the pandemic, actually. Just by analogy, I was wondering, if you get to wonder, how can the oil field be operated in this manner? And if we have appropriate data, let's say, can we meld our conventional wisdom in terms of physics and say we can combine them with fit-for-purpose analytics to make better decisions and even so more consistently? So I'm Satish Sankaran with Exacta Digital Labs. I will be talking today about fusion of physics and analytics with applications in oil and gas. So I'll start with the state of analytics in oil and gas from a practitioner's standpoint, from an industry viewpoint, on where we stand, and at least my perspective on that, and some challenges that we need to overcome. This is a broad area, so we will touch upon maybe a few, but tangible examples that we had implemented recently, and also share our views on areas that I believe would need probably further research, future work in terms of technology maturation, and eventually adoption within the oil and gas industry as well. So when it comes to analytics, there are many belief systems on what the right approach is. The word cloud here actually shows a varieties of terms and terminologies that we have been using in the oil and gas industry to describe many of these methodologies. So what exactly do we mean by data analytics? If I were to borrow the words of the Supreme Court Justice Porter Stewart from the landmark case in 1964, he said, "I know it when I see it." But for purposes of this talk, we include all these methods where we work towards one common goal, that is, deliver insights to help humans make good decisions. But why now? So what has happened in the world that makes analytics and broadly AI relevant to oil and gas industry? And of course, technologies have vastly improved over the last decade in particular, that this audience probably would need no further explanation, especially in the world of sensors, communications, algorithms, hardware, etc. But more importantly, on the business side of things, in oil and gas has vastly changed in the last decade. According to EIA, about 63% of the total oil production last year in the US was produced by unconventionals. That includes low permeability shale, sandstone, and carbonates. Just the sheer number of wells and the supply chain logistics that need to be put together, that requires a massive level of operational efficiency. The silver lining here is that we do collect a lot more surface data from the wells that are drilled. And then there are the success stories and the transformations that we see in other industries, in finance, healthcare, like the example that I mentioned, or others actually, where we see the value of data-driven decision making. Can that inspire us to make oil and gas operations, let's say, more profitable under low crude oil prices, such as what we are seeing now? Even before the current slowdown that we are seeing over the last 2 months, a lot of unconventional operators have been struggling to make positive cash flows. And then there's the issue of safety and other regulations around emissions, etc., that we also need to be caring about. All these changing requirements have created what I would call as a perfect storm in the upstream industry to rethink the way we do business. That's easily said, but changing the way we do business is not that easy. There are other challenges. First, we have to deal with the data issues, including collection, processing, storing, organizing them, labeling them sometimes, and then also retrieving these massive volumes of data that we collect on a day-to-day basis. For example, in a modern offshore platform, let's say in Gulf of Mexico, US, we collect about 1 billion plus data points every year just from subsea and downhole data. And when we were executing some projects, we realized that less than 5% of the data was even actually used. And then there are other contextual information that goes along with that, such as where your well was drilled, attributes of the reservoir properties, etc., which don't even have proper data stores. There are some open project initiatives that are going across the industry right now, such as Open Earth or OSDU, the Open Subsurface Data Universe, that are trying to address a portion of that. And some companies are also developing massive data lakes, actually, to support some of their internal analytics initiatives. But then a data management project without clear goals or end in mind or the use cases is not destined to succeed in the long run, actually. And then the wells that we drill are becoming also more and more complex. We also have a diverse and distributed workforce, especially since the last downturn. There's also a significant experience gap, actually, if you look at some of the industry statistics. Institutional knowledge and experience, such as using some of the classical methods, etc., for running an oil field. Some of these people have walked out of the industry, either retired or lost their jobs, and it's happening as we speak right now, especially under these stressful circumstances. In reality, many top companies now, they have lost their experts in core functions like code analysis or fluid sampling, well testing, etc., without even having proper knowledge transfer to younger staff. Besides, companies have to deal with the scalability of all their internal work processes with the resources that they have got left. Both financial capital and human capital. Basically, we need a new way of dealing with all this, manage more wells than before with less experienced staff under the most challenging circumstances, but still make good decisions. So what is the opportunity? The opportunity here is to see how modern digital technology can help us. First, can we quickly monitor, analyze, and optimize our fields? Second, can it make us more disciplined with our capital spend and also operate in a socially responsible manner, thereby creating value? And third, can it help us standardize at least the routine work processes, the number of mundane tasks that an engineer does, so that we can augment him or her to work more efficiently, basically combining human judgments with machine intelligence. Now, the oil and gas industry has been exploring and investing in a bunch of different technologies over the past few years. Notably, I want to highlight that the big data and the analytics and the AI elements that you see over here are things that have not only a greater capital spend, but they also have large growth prospects as we look forward. And then there are other technologies that enable them. most of the actual project implementations in the last few years have come about in the mobile devices, IoT in particular, and then the cloud, etc. Even though a lot of people are talking about cloud, but I would say that I mean, most of the back office functions are probably slowly moving over there. But when it comes to petrotechnical applications, we are not quite there yet. Actually, the people are still in the very, very nascent stages of that. And with IoT, the challenge has been infrastructure to make them feasible, such as power, communications, especially in remote areas like offshore or West Texas and so on and so forth. So now, this statistic is from a few years back. So what has happened since then? Within the operating companies and service companies, nearly 80% of them have some kind of digital initiatives of sorts. The boldness of the vision may vary, or what they consider as transformation may have a wide range. But 70% of the companies have either created or partnered or collaborated with some kind of a data science group or centers of excellences. Some of them are also starting to include data science as a recognized competency for engineers within their own companies. There's also a significant surge in what they call as digital work products or digital oilfield technologies or industrial revolution 4.0 products, etc., that are either purchased or developed internally. In a manner of actually, if you look at R&D that was once outsourced from operators to service companies decades back, they are now coming back. I would say especially or more focused so in the analytics space. Meanwhile, in the broader industry, if you look at the societies, they are all now organizing many more events, catering to the demand for all these analytics programs. There are dedicated publications such as data science and digital engineering newsletters and journal articles that cater to this topic, I mean, quite a bit nowadays. There is also a new core technical discipline that was introduced in SPE recently, I believe late last year, called data science and engineering analytics, especially to serve this audience. And then there is an ongoing recent effort at publishing the first SP technical report on data analytics and reservoir engineering. There are training curriculums and data analytics courses that are being generated targeting petroleum engineers, including Shrikanta and other people who are actually teaching some of these courses as well. And then in academia, we also see many newer faculty in universities working on cross-disciplinary research, bringing in AI and machine learning components into petroleum engineering departments. Some of them have actually generated some excellent approaches, both in geoscience and reservoir modeling, that are very, very promising. So the vision here, I would say, is to create a framework within the upstream industry that seamlessly allows a decision hierarchy. And by that, I mean decisions can be made that are made at multiple timescales across the supply chain at various stages in the life of the field. They all come together seamlessly. And then decisions made at higher levels are passed down as optimum targets that cascades down and eventually to the field operations. Whereas actual or observed data is consumed in a feedback loop to improve the models, recalibrate them, or basically iterate to make new and better decisions. The final goal here is basically to optimize the asset performance at all levels by measuring, modeling, and analyzing all the data in relevant time being subject to the phenomena that we are monitoring across the entire value chain. In oil and gas applications especially, we have been dealing with physical equations for several decades. Some of them are very, very old and being field tested adequately. So what is the role for data analytics, and when do they add value? So in principle, I would point to maybe three major application areas. First, when the physical mechanisms that govern fluid flow, or let's say fracture propagation or interactions between, let's say, some of the multiphysics processes are either less understood or impact the model fidelity or the accuracy. And then we ask the question, is the model useful in its present form, in its set of equations, that we can use it for something meaningful? The second area is, even if we believe in the underlying model, if you think that we understand the mechanisms very well, do we have all the inputs required to characterize that model? For example, geomechanical modeling has been an area of active research for hydraulic fracturing and primary production. People, especially in unconventionals, and people use a variety of approaches. I mean, there's not much consistency around the industry, around best practices yet. However, going with any belief system of how fractures are formed, propagated, and behave we still need a lot of inputs that are just not collected at every well in the basin. That substantially limits the number of wells or well paths that can be modeled and analyzed effectively. And then finally, even if we have a model with the inputs, it may still take a long time to build them, calibrate them, or history match them, and then analyze, and then eventually make use of it by maybe generating recommendations, etc. The field decisions, especially in US onshore operations, need to happen at a much faster time scales that are just not possible with physical models alone. And the natural fit here for AI or analytics-based models, or a combination of them actually, is when either one of these conditions are not feasible. In the next slide, I'll talk about some examples of where they have been applied within various disciplines. I just want to acknowledge that this is by no means a complete list, but these are just some of the areas that I'm familiar with, having worked on a few of them actually. In geoscience, there's been a surge of research, especially in identification of anomalies in seismic data, leading to faults or salt identifications. This is the area of deep learning, where image processing techniques are employed through transfer learning and other methods, actually, with some domain tweaks to improve the success rates. And then there are a variety of applications of classification that are used for EOD mapping, environment of depositions, and then phases recognition, and so on and so forth. And then TOPS propagation is another cool technique that is used to automate the geological correlation process that can process thousands of wells now just in a few hours in an onshore setting, compared to the manual process that takes several months. And then in petrophysics, there are other applications such as QCing log data, correcting bad values based on local machine learning models, or also predicting well logs based on training data sets for missing properties, and so on and so forth. In reservoir engineering, estimation of properties such as fluid and core, it's been going on for a while. They have been empirical for a long time. But with proper data management now and availability of some of these other new methods, this is also becoming more possible in a more organic manner, both within the operating companies, but also within the labs themselves. In unconventionals, most companies employ some sort of multivariate analytics that correlate geological, geomechanical, fluid, completions, and also eventually production data to make decisions on their well placements, such as targeting, spacing, both in 3 dimensions, but also in time, which is the parent-child effect, and the completions design aspects. And then in conventionals, there are newer methods that are exploring how to incorporate machine learning into fast-tracking this reservoir simulation work, so that we can run many more simulation runs, and we can run optimizations, and then run several scenarios, etc. I'll touch upon today on some examples on the reservoir management side using some hybrid techniques. In drilling and completions, in general, most applications are geared towards operational efficiency gains, with some kind of emphasis on surveillance type of applications. People are looking to estimate drilling parameters that they cannot measure directly, such as downhole MSE or pressure losses, or identifying drilling dysfunctions before they happen. And in completions, there's a rich amount of high-frequency data, especially stage-based stage data set that is ripe for analytics, and it's largely untapped, actually. On the production side of things, things have been a little bit more mature, automating detection of well events, such as shut-ins, when a well test happens, when it's flowing in steady states, etc. They allow or enable exception-based management. There's a new set of methods that are emerging for automating well performance estimations that were largely done manually before. There are other applications here also around emissions monitoring and pipeline leak detection, both in the context of onshore and also deepwater offshore applications, especially since Macondo. And then finally, in the facility side, I would say upstream and midstream, actually, we have tons of high-frequency process data that lend themselves to equipment health monitoring and predicting impending downtime with sufficient notice, so it can be avoided or at least gracefully handled. This is also a secondary effect, actually, in terms of cutting down emissions and so on and so forth. So we've seen all these applications within oil and gas, but what's the catch? The issue is that many of these things are not widely deployed or operational yet, or we do not have sufficient know-how in terms of how to scale them. There are many reasons. First, while we have plenty of high frequency data, it may not be relevant data. For example, if you're looking for certain kinds of events, say in the pipeline leak detection example, we need actual leak events to train these models. That is small data actually. So, or in another example, we may look for productivity impairment to wells, productivity decline in wells, which may not happen as often, and even though we may be collecting high frequency data. Therefore, the context of the use case in which we need data may present in certain conditions, at least sparse data, and sometimes also quite uncertain actually with noise and all the other measurement errors. For example, with fluid properties, we measure or conduct lab PVT studies on less than 5% of the unconventional wells, take Permian or Midland Basin or so on and so forth, in general, but we need to extrapolate any model-based estimations on the remaining 95% of the wells. Do these models generalize very well? In some circumstances, we may offset the data shortage with simulated data, provided that is relevant. Another major class of problems here is around the inverse problem and the non-uniqueness of the estimating model parameters. Of course, this is not unique to only data-driven or analytic techniques, even for physics-based models, but then human judgment is sometimes used in making those engineering interpretations. So how do we incorporate that knowledge into any automated algorithm? Many of the decisions that we make, at least in oil and gas, are very expensive, I mean, both direct cost and also the opportunity cost. Therefore, we need reproducible methods. If an engineer were to repeat the modeling analysis, let's say, are we able to reproduce the results that make it auditable? And most importantly, are we able to explain the results? This is a huge topic of concern in many companies today that I have witnessed myself. I mean, for example, an engineer or a data scientist may have a more accurate machine learning model that probably involves some deep neural networks or so on and so forth. However, since the neural network is a black box model, it often gets superseded or ignored. In lieu of that, probably people are using simpler models that may not be as accurate, but are just more intuitive, physically intuitive and interpretable. In a way, this may be a healthier and desired option for humans to work alongside AI algorithms, let's say, since otherwise we need to be able to consume the models and explain it and understand what's happening. Otherwise, we would just be, let's say, trading bureaucracy for algocracy. I mean, where algorithms tell us what to do without us ever questioning them. The desire here is basically just to have machine intelligence augment human understanding and engineering judgment to improve operations and not to replace it. Having said that, let's look at some of the modeling strategies in the context of reservoir modeling. First, I would like to submit that the modeling framework is not a dichotomy, and it's rather a continuum. The path that we take with any of the modeling approaches is just a means to the end. The goal is to take the best of both worlds, basically model fidelity, accuracy, explanatory power, and extrapolation capability that we have with physics-based models, and combine them with low complexity but fast models that can be used for quick decision making. The second point here is that companies spend a lot of time, effort, and money actually collecting a lot of data through the data acquisition programs. And in the modern day context, actually, it's more real-time feeds actually and measurements. The necessity in this context of data getting more real-time is that the model calibration should also get more real-time, without which the traditional physics-based models are just unworkable. So in this sense, and as autonomous calibration and prediction, I mean, they become more of a necessity, and the volume of assets that we have to manage increase substantially, such as in shales. And these methods, such as reduced complexity, reduced physics, and data physics, etc., I mean, what I call as hybrid models in here become very, very important, and probably in some cases only the only option. In the next few slides or so, I'll present 3 examples sampled from these hybrid models with some case studies using physics-based features, dynamic drainage volume using the concept of diffuser time flight, and also reduced order models. So the first example, we have a conventional reservoir, and the objective here is to infer well performance and detect if there is any productivity decline from routine production data, that is without shutting in the well. Here's an example of the well profile showing bottom hole pressure in red and the liquid rate in green. And normally the reservoir engineer requests a planned shut-in for a few hours and then performs a pressure transient analysis to estimate reservoir properties such as permeability, skin, amongst other things. Also, under flowing conditions, one may perform a production well test to measure the individual flow rate, phases flow rates, and or use it to compute well deliverability or an inflow performance curve. However, these events happen very infrequently. I mean, if you are lucky, we may have one production well test a month. I mean, that is if the regulation demands it. The planned shut-in tests sometimes are even more infrequent, maybe one a year or twice a year if you are really, very lucky, especially the well produces at high rates and nobody wants to shut them in. However, in the normal course of operation, the well does go through a lot of changes. Actually, for example, in here we have a stable flow followed by shut-in, followed by ramp up, and then a choke change, an operating point change, etc., etc. And there is information in all these time periods as well. So can we deconvolve and estimate the well model from pressure and rates alone? So okay, so if you look at the classical methods for such analysis, we use a forward model. We propose a transient model, and then we use some kind of a diagnostic plot like log-log plot or similar, and then propose various flow regimes, radial flow, boundary dominated flow, extra, and then sometimes additive, and then we perform some kind of a regression to match the model parameters. But this process, first of all, is highly interpretive and done by the engineers in an iterative manner. And now that we have bottom hole gauges ubiquitously available, actually in most wells, we have far more real-time data. And these are not just planned shut-ins, but several unplanned shut-ins, but they are opportunistic as well. So can we analyze all of them and in some manner have the machine kind of automate that process? Deconvolution is one such technique or inverse modeling technique that we could use. But at the moment, if you look at all the algorithms that are available, they are still anchored to a reference buildup actually. And they are also greatly affected by noise in the system, amongst other limitations. I mean, not to mention, this is also a manual and iterative analysis, right? So what we are in the lookout for is an approach that kind of alleviates some of those pain points. So our solution approach here is to take inspiration from the classical analysis and post the flow regimes as features and that are encapsulated by their characteristic time functions. So we create these physics-inspired features, including the superposition effects, and then we can post that as a regression problem, actually then find parsimonious models, actually. So by doing that, we have fitted just from rates and pressures that we have observed, we have fitted a model. We are kind of taking a similar approach, but instead of doing it through a hypothesis, we are trying to impose all the flow regimes simultaneously and then picking out the ones that matter. So how does this method perform? So on the left over here, we see some training data for about 15 days. Liquid rates are shown at the top, and pressure drops from the initial condition. For a deep water well, in this particular case, we use rates and time to calculate pressure. With the trained model, we can predict the pressure for some new rate profile, which is shown on the right-hand side. Notice that in this data set, actually, we do have a shut-in, actually. So, and then the well has seen some unplanned shut-in, so we can also compare it against the classical methods. First, the prediction in red matches the observed data blue quite well, using the method that we just talked about earlier. And the last plot in here actually shows the classic Boudet derivative plot or the log-log analysis. So where we show that we also preserve the flow regimes actually. So this is good validation of not just the model accuracy, but also now it can be physically interpreted actually. So using traditional techniques. Okay, so this is reconstructing pressures from rates. Now we can invert the problem and provide pressure as inputs and then calculate rates actually. So, and the purpose of doing this is to create a virtual meter in the absence of a multi-phase flow meter, or to verify if the meters themselves are going out of whack or needs calibration, etc. So we have about 20 days worth of training data for the same well, and we're predicting 10 days here. Again, we see a very good results, especially at high flow rates. At low flow rates, this is a cross plot comparing predicted versus actuals, and low flow rates we see some deviations, and that's mainly because we don't quite reach predict all the way to the bottom over here, or coming down to zero. Again, for this use case, it's not as important because the focus was on understanding well performance and tracking productivity decline at high rates. And then finally, now that we have a trained model, instead of relying on just field shut-ins, we can simulate a shut-in with that model, or we can do a virtual shut-in, and we can perform any traditional, use any traditional method to analyze the data and then calculate PIs. So in this case, we automated that process and compared them to actual shut-ins for a period of about 1.5 years. The actual PI is shown here in red, and the calculated PIs are shown in blue, and we can conduct it at any frequency that we desire, in this case on a daily basis. And we see a very good match, number one. Now, this can also become a good diagnostic tool for the reservoir engineer to plan, let's say, future buildup tests, let's say on an exception basis, while still having a continuous handle on the well performance that is used with just routinely acquired data. Now, while this provides benefits in terms of, let's say, avoiding production deferment in terms of shut-ins, we also have now a method that kind of self-calibrates and meets the data volumes that are obtained from these downhole sensors, both unplanned and planned shut-ins. It's also important to talk about limitations. The method relies on natural dynamics that happens all the time in routine operations. So that's a requirement. In this example, we had only one well, but if we have interference from other wells, for example, the number of features can grow very fast, and it will require some amount of consideration to come up with the right type of parameters and do additional tuning and so on and so forth. So that's the first example. In our second example, let's consider an unconventional well with low permeability. Here we have the same objective, basically determine well performance, but the problem here is we are in mode most of the time, and the rates are constantly declining. The industry standard to analyze these wells is rate-based decline curve analysis, and there's a lot of new decline methods that have come up recently. However, most of these methods are strictly valid only when there is a decline, or in other words, there are no substantial surface effects that are constraining production, and also the bottom of pressure is held constant. But in real life, this doesn't happen, especially due to all the surface operational issues and shut-ins. For example, many unconventional wells are being shut down right now, due to oil prices, and this is a hot button issue in the industry about if these wells are going to come back to production levels, at the same levels as before. However, when they do come back on, are they going to even behave similarly? And there's concern around stress cycling and its impact on the fractures and so on and so forth. Naturally, just the sheer gap in production and the flush production that you're going to see with the reservoir recharge is going to impact all rate decline based curve forecasting methods, and consequently all the reserves calculations coming up as well. So what can we do about it? Most of the unconventional wells are not instrumented with downhole sensors, but we do have surface gauges, and we can estimate bottom of pressures. With that, one can perform, let's say, rate transient analysis or numerical modeling. If you have other reservoir and fluid properties also available, but then these methods don't scale very well, and it's not feasible to do that for every single well in the field, actually. So in this case, our solution approach was to use the concept of diffusive time of flight that was developed at NCERI research team at Texas A&M. We have adapted that technique to automatically calculate drainage volume as a function of time using a geometry-free approach. So basically, as the pressure fronts propagate away from the well, even for a heterogeneous reservoir, we can estimate the volume enclosed by each of these pressure contours as a function of time, just from routinely measured variables like rates and pressures, in this case, bottom hole pressure. Now, this opens up interesting possibilities. So in order to just understand the well performance, we first solve the 1D diffusivity equation to estimate the size of the drainage volume. We show here how the drainage volume kind of evolves with time, which is monotonically increasing. Note that we don't specify the geometry or dimensions, actually, only the total volume, right? So next, what we can do is we can take the first derivative of that, and that can give us a look into how the evolution of the surface area is evolving, especially to understand the various flow regimes. And finally, we compute the ratio of cumulative produced volume to the dynamic drainage volume, and we call it as the instantaneous recovery ratio. That helps us understand the effectiveness of the completions also. Now, this is important because we can now create diagnostics that are consistent across all wells and are generated automatically. Here's one such example. Now, by performing clustering of these wells, we can now look for sweet spots or understand maybe correlations with geologically favorable within geologically favorable areas, etc. Further, we can also now apply material balance using a succession of pseudo steady state approach, because we have a volume kind of estimated over a function of time. And then taking those different snapshots, we can estimate pressure depletion, which is the plot on the left. And by combining that with actual production, we can also calculate a transient PI or a productivity index. And we have run this on actually thousands of wells in Permian Basin and in the Rockies and Powder River Basin, where we see the same shapes show up again and again, actually. So we have normalized the effect of surface operations in a way, and now we can estimate trends in the PI that can be used to forecast also into the future more robustly than just a rate-based approach. And with that, now we can use a PI-based forecasting as an alternative to rate-based forecasting. So how do the results stack up against those incumbent methods? We did a blind test at the end of 3 months, 6 months, and 9 months, respectively, on multiple wells. And consistently, the PI-based method had less error, and more importantly, we were able to establish clear trends even earlier than the rate-based method, especially when there is some kind of a choke back strategy or other things that are going on with the wells. On wells that have been choked back as far as concerned, in fact, the only method that was applicable was the PI-based methods. Now, the PI-based forecasting method is automated and can be applied consistently across all the wells. It can take away the human bias. It can also help us with planning artificial lift and other things as well. But strictly speaking, from a limitation standpoint, this was a single well analysis. So we have to extend this method to account for multiple wells, such as when you have interference due to brackets or even spacing effects, etc. Some interesting things that we have observed is that on a PI, transient PI estimate that we have, they show up distinctly as blips, actually. So this becomes also a diagnostic tool for detecting interferences between wells too. And because we have been using a 1D method here without reference to any shapes, the method does not really resolve which well was interfering with it, and that will need additional context. Now that's example 2, and then my last example here is on is a problem for optimally producing a bunch of wells that maximizes the overall reservoir recovery, either in primary production or secondary recovery like water floods, etc. This is a classic reservoir management problem, and numerical simulations we know are not quite conducive for continuously calibrating and updating and running optimization on a daily basis. So effectively, what we are looking for are some fast models that can be used for forecasting production for the various pressure control strategies that we may think of. Also, the optimization problem in this case can also be very large because the time-dependent pressure control, because there's also a time element in it, the number of time steps would significantly explode the number of decision variables over here. So we need to have some models that can be evaluated very fast. So in this example, what we try to do is we start with a handful of simulation runs. In this case, we are saying that we are starting with a simulator, run a handful of carefully selected simulation runs for different production strategies, say bottom hole pressure controls. We take snapshots in time of the pressure and saturations of all the grid cells. We stack them up together and call it X. And then we offset the columns by one time step, and then we call it X prime. And we do the same thing with the inputs. In this case, inputs are the bottom hole pressure, and then the outputs for us Y, which is all the well rates that we want to predict actually. So we then perform a modal decomposition using a variant called IODMD, or input output dynamic mode decomposition. Effectively, what we are doing is we are computing a set of modes that have fixed frequencies. This differs from the dimensionality reduction methods like PCA, principal component analysis, or similar, which may produce more parsimonious models or smaller models, but GMD provides more physically meaningful modes actually. So effectively, we have simplified the numerical simulation model with a linear state space model of much smaller size. Now, with IODMD, we can now take advantage of the coherence in the pressures and saturation evolution between all these different cells. And we have reduced the order of the model. Maybe the simulation model was millions of cells, and then we have converted them into like maybe an order of hundreds or thousands actually. And with the linear state space model or the ROM model now we can go forward and predict any initial condition, how the pressure and saturations are going to evolve for a given set of well conditions. And then in one DMD variant, what we have called DMD with control, we use a random forest machine learning method to mimic the well index or the Piesman equation, and then with the IODMD formulation, we explicitly calculate that output, basically the rates directly. The plots on the right over here show both the spatial variation and the temporal variation or the time evolution of the rates in this case, and the saturations over here. They match quite well with the observed quantities. Note that in this case, we only needed 2 or 3 simulation runs to train our model, as opposed to other pure data-driven methods where we have to need a lot of training runs actually. The ROM model here was also much faster, 30 times faster than the original simulation model. And more importantly, now we can also reconstruct back from this reduced order model. We can reconstruct back the entire grid, and so that we can visualize how the saturation profiles and pressure profiles are also evolving over time, and that significantly helps us with interpreting the solution and the results. Here's another example where we applied the same IODMD method. In this case, we applied it to a deep water facility for a process separation frame that separates oil, gas, and water. Here, instead of using a simulation model, we directly use the field data because we did collect them from our historian from various sensors. We are interested in taking the inputs to the facility, which are the input feed variables, and then correlating them or being able to predict what comes at the outlet in terms of the produced quantities for the oil, gas, and water. And we want to build a dynamic model that can be used to analyze things such as slug control or different operational strategy for changing separators, pressure and temperatures, and so on, etc. So again, here the ROM model performs quite well. It provides actually a viable alternative to building and maintaining a detailed process simulation model in this particular case. In both examples, we used a non-intrusive method that can work quite well with black box simulators or even field data directly. In particular, we can in the first case, we can reconstruct back the entire grid and explain the results much better because we are following linear dynamics with explainable models. However, I mean, there's no free lunch. There are limitations on when and where we can apply these modeling techniques. We need to know the well locations ahead of time. So we can't use it for infill drilling optimization. We are using it for production control optimization, rate control optimization. Also, when we reduce the order of the model, we don't explicitly guarantee stability, and it's somewhat iterative at this time, I think, which could be further improved as well. In the next few minutes, I just wanted to reference a couple of new methods that are emerging in the last couple of years especially. Physics-informed machine learning refers to a class of methods that were initially developed as neural networks that are trained to solve as supervised learning tasks, but simultaneously constrained by physical equations or PDEs. For example, the objective function for the learning task here is formulated as a loss function in terms of data mismatch plus mismatch in satisfying the PDEs and boundary conditions, initial conditions, engineering controls if we have any, and then any expert knowledge that we may want to impose. If we have observed data at certain points in the manifold, say either over time or over space, those could be brought in as well to constrain the solution. Now, and there are many more variants of this, including some work that's been done within the national labs themselves. PIML fundamentally addresses the problem of small data while honoring physical principles and at the same time providing more realistic solutions that can extrapolate reasonably well. It addresses the solution of generalization. There is still a lot of work that needs to be done over here. In the context of reservoir modeling, however, we don't often collect data at high spatial resolution, and therefore, I mean, it may need a little bit more work to see how we can extend the application of these things so that we can use it, we can constrain the solutions more realistically. So I shared a few examples of how we could bring together physics and analytics from a technology standpoint. I mean, there are some promising approaches. You can say new solutions maybe to old problems. We still have a long way to go. I just want to close by talking about where maybe some of the future efforts could be directed from an industry needs perspective. I would like to highlight maybe 3 major areas. First category, we have the discovery of new algorithms or methods, basically new technology development. For poorly understood mechanisms, this may include discovery of the governing physical equations themselves. A good example is unconventional coupled fluid flow, combining, let's say, geomechanical and fluid flow equations and how they behave over time. In cases where we have only limited data, can we include some physics to constrain that solution and still make it useful? So again, for example, when we have water disposal in unconventionals or CO2 storage, we don't often collect a lot of data actually. So we have to deal with a small problem, and we still need to fast forward some of these or accelerate some of these models, and we need to have effective methods of doing them. And third, we also are seeking algorithms that can actually accelerate the model runtime substantially to keep with the pace of many things. So, for example, I'll take the pipeline network optimization example. They are traditionally modeled using nodal analysis. This technology that we use today in commercial simulators, they have not evolved much over the last 20, 30 years. We have known them for a long time, actually. But with new developments that are happening in distributed optimization or agent-based optimization and graph and network analytics, etc., can these methods be improved? Can they be made to run much more faster so that we can solve large networks much more quickly? In the second category, we have technology maturation. So once we have some of these different methods, we still need, I believe, some industry benchmarks for new mature technologies to be proven against some, let's say, common or shared data, at least for common functions such as forecasting and water floods as examples over here. At the end of the day, people need to trust and make sure that the method is robust, that they can go ahead and use within their own applications. Beyond the accuracy or the fidelity of the models themselves, we also need to pay real attention to the interpretability of the models. At the end of the day, we are enabling a human being to make decisions as a recommendation, but that comes from these models, and they can only do that if it can intuitively understand it and know why the model is performing certain actions. Building that human-machine interface and explaining that model will significantly help in user adoption. And that brings us to the last category over here. To promote adoption, the hybrid methods or hybrid models and bringing physics and analytics together needs to find its niche and also its way into the business process itself within the companies. Otherwise, they would always remain an optional element or a ad hoc analysis and not mainstream. For example, a proper decision support system could be supported by these hybrid models, but that can help with their data analysis, identification, and let's say even design of alternatives, evaluating those alternatives, and eventually recommending the best options. Companies are realizing these needs today, especially because of the changing business requirements that I mentioned upfront. But they would need to put together a comprehensive competency development for their employees. I know some companies are trying to do that already. Shell, for example, has started reskilling most of its employees in AI on a voluntary basis across upstream and downstream. Amazon does that, offers free data science classes for all its employees, and many more companies are doing that. And last but not the least, over here, there is also a need and a role for the technology vendors as well to provide easy-to-use commercial tools. While the oil and gas startup ecosystem has really taken off over the last few years or so, there are many niche players, and there is still room for improvement to provide more robust and also domain-specific applications. So, and with that, I would like to thank you for your time attending today, and we'll be happy to hear your feedback as well. Thank you.
Thank you. Anybody that wishes to ask questions can unmute themselves or enter them in chat.
Hey, Satish. This is Rajesh Kaur at Los Alamos National Lab. Nice talk. I have a couple of questions. On your last slide, you mentioned about training and basically virtual learning, so to speak. Are you aware of any virtual learning environments, especially related to reservoir management, that companies have been developing?
Okay. A few things that I'm aware of. Some companies have tried to do this internally to themselves, actually only for their own employees per se, actually, but they are very, very niche and very focused on their own specific operations and the tools that they have developed, and they provide training programs on top of that. They may have developed maybe a tool that uses a flow network modeling kind of approach, and then they provide training to their employees on that, etc. And then SPE also is developing a curriculum, a broader curriculum for training across multiple disciplines, reservoir management being one of them. And they're also doing that for production engineering or artificial lifts, drilling, etc. But that's something just coming. There are also a couple of other courses that are already existing in the SP space that kind of addresses the data-driven modeling more from a foundation standpoint. I would say, and then there are universities that offer some core courses, but I wouldn't say they are still geared towards the need of the hour. Basically, what you're asking is there something that already ties that directly to the reservoir management aspect of it with practical examples? If we were to extrapolate that, I would say that in a public setting, that's under progress.
Okay. And then the other question was going back to your reduced order model or application. Now you did mention the limitation of it in terms of having, basically underlying this is you need a calibrated model, or at least that's where you see it being more effective. Have you looked into or explored the possibility where you start with a model that is calibrated to certain data that you have available, but then you adapt it or it evolves as you get additional data, and then you can basically improve its applicability in the domain where you are extending beyond where you have calibrated, and especially for CO2 storage, that kind of becomes something. I mean, that's an area that would be of interest where because as you mentioned, there is only limited data that is available, and so you are going to start with models that are especially the AI-based models or machine learning-based models, reduced order models that are calibrated to data, limited data, but you do want to see how they evolve as you start collecting data.
Yeah, actually, a good point. So one of the things that I have seen, and also we have done some work on that also, is instead of trying to keep one or the other, that is either the physics-based model or the other one actually. So we probably, in some sense, we can combine them together. We can use the we can, in the context of the PIML approach, actually, we could maybe mix and match them in various ways, and then we could model the residuals instead of having to model the absolute numbers itself. That's one approach. Or we could have a library of models, and then we can see which ones apply to certain areas. In the context of reduced order models, one challenge that we have is when we do the history matching, so to speak, on the reduced order model space, for example, we could fit in this context, what I was showing, the ABCD and matrices, basically the state space matrices. There is not a clear way of, I mean, we have projected it to a lower dimension. Going back is not that easy. But having said that, as we look through, there could still be some physical insights in terms of what we could see how the profiles themselves are progressing, because we can still project it back into the full dimensions. There may be other approaches, I mean, as well, actually. So, but I mean, these are just some of the things that I have looked at.
Great, thanks.
Thank you. Okay, the question is, in well testing, how can you ensure that a good training data set is being used? For example, if the training data did not encounter boundary dominated flow, then the predictions will be significantly off. Yeah, absolutely. The data that we use, basically the bottom hole pressure data and the rate data that we see, should have seen those respective flow regimes actually. So therefore, in all the examples that I showed, we use, in this case, this was a deep water reservoir, and we use at least a few days worth of data. And these are high permeability reservoirs and high flow rates actually. So therefore, it has seen the limits of the bound of the reservoir in that sense. But because of all the routine operations, you are constantly having transients. They have not established a steady state, right? So in that sense, we still have, I mean, that is an absolute requirement that we need to have dynamics in the data to detect it, but it should also be representative enough that it has seen all the flow regimes that we want to include in our features. The next question is, will you have a copy of this talk to be made available? Yeah, yes, from my side, and maybe Terry or Gavin, you can see how to do that actually.
Are there any other questions?
So if not, this is Shrikant once again. Satish, thanks very much for a very interesting presentation. And thanks for making the time to share your expertise and insights with us.
Yeah, thank you very much, Shrikanta, and everyone for attending as well. Thank you very much.